Continuing with this series of videos, something around lecture 14, Professor Lewin, electricity and such. Maybe I'll do a little bit of a pre-drawing thing just to clarify something about this idea of what's moving through the wire, the pressure. So, voltage can be very high, and it's transferred in essentially the same process as very low voltage, except there's just these few transfers that take place. So if you had atoms, and I don't know how to quickly draw this, so I'll just draw it some kind of less quick way. I guess we'll just make these protons down here, try to illustrate this in some way. And so you have let's call these the shared electrons. They're the same size, not really different size. So they're shared in the sense that there's pressure between them in the chain of atoms. And what's basically happening is electrons are showing up, and they have a speed, and which is essentially equal to this idea of pressure. So when they come in, they create a great deal of pressure. So if you have high voltage, what you're really doing is pushing an electron vigorously, and that pressure is transferred to the other electrons, and essentially just moves through the pressure of the electrons. So the movement of the electrons doesn't even have to be substantial in any way. It just has to be this little bit of movement that creates more pressure, and the pressure just moves through the atom. So you could have 10 volts or you could have 100,000 volts, and the difference is how much pressure you're pushing through these electrons effectively. So it's in a sense the speed of the first impact. And at one end of the conductor you always have the fact that you're pushing. Okay, so you have the high pressure at one end, and the other end is where the pressure is received, which will eventually be a high pressure, but it's clearly not there yet. So essentially, as the pressure moves, you could sort of understand that when the pressure's at this location, let's say, then this atom is a positive ion. What would be called the negative ion, actually, the higher energy, the higher potential. And then this one becomes the negative ion, and so on. So as it transfers, that's where the polarity is created, where you have this pressure difference between the atoms, and essentially creating the reveal that will be this atom. If this pressure is high, that means the electrons are close together when there's high pressure, and this atom is viewed from the rest of the world when the electrons are close to the surface as being decidedly negative from the external world. When there's low pressure and the electrons are further apart, it's viewed as a positive from the external world, just because of the proximity, the size of the ring, you could say, between the center of the atom and the circumference of the electrons. And so the electrons are blocking more of the proton when they're close together, and they're blocking less of the proton's energy when they're further out. So the further out you put the electrons, the less energy of the proton they block. You can sort of understand that it's a tiny fraction when they're far apart, and it becomes more and more of a cone of blocking as they're closer. So that's the difference between a positive and a negative, or a polarized versus an unpolarized atom. It's not just about how many electrons there are, it's about how much pressure they're under. size matters. In this case and most cases. Yeah, so I think that's enough of just for clarification. Just for clarification. So, moving on, I need to move this back down. Alright, that looks correct to me. So, off to the video.
Equals VA minus IR. So if there's no current going through the wire, no one is using any electric energy, then VB is the same as VA. Now I want to know if we consume energy, so we're dealing now with power. So the power that we take off at Boston is I times V of B. That's the number of joules per second that we are consuming. So that then equals VA times I minus I square R. It's fine. What is this? This is the energy per second that we are consuming. What is this?
Voltage times current with the B thing. I don't know what the B thing does exactly.
This is the energy per second that the power station is delivering to us. What is this? That's lost energy. It's the I square R, it is the heat produced in this cable. It goes into the universe, it's gone.
Right. I guess it's in all kinds of radiation. This heat can be manifested as light. So, you know, it's... But yes, it's not progression of the pressure. It's where the pressure doesn't progress and gets caught in the conductor and is disposed of by the process of the atoms absorbing it in one form and releasing it in another.
So the economy demands that we try to make this as small as possible. So this is the power that is available, but you get a loss of power in terms of heat, the minus sign here. So you get less in Boston. And so how can you make this I square R low? Well, what is the resistance of a wire? That is rho, which is the resistivity, times the length of the wire, divided by the cross-section of the wire. So you have several options. You could make A very large, a very thick copper wire. That's expensive. You could also make the wires out of gold. That has a lower resistivity than copper. That's also expensive. People are thinking of making these transmission wires of superconducting material. They have to cool them at very low temperatures. That's outrageously expensive. But that's the way you could get the resistance down. Let's now look at the current. What can we do with the current? Suppose we consume 100 megawatts. Not an unreasonable number. So we are consuming 100 megawatts. And just for the sake of the argument, suppose at VB the potential is 100 volts.
Again, the resistance has to do with the exchanges. So every time an atom exchanges, you could say there's a certain amount of resistance or likelihood that the atom won't make the exchange properly. And that's your heat, that's your resistance. So anything that disrupts the process of the migration of the pressure from atom to atom, like the wrong kind of atom being in the arrangement, one that doesn't transfer pressure, it's not connected, there's space between them, some obstacle to the transfer. That's the resistance. And so you encounter the resistance, the more exchanges you make. So if you're at low voltage making lots of exchanges through the wire, you have more opportunity to create heat. But if you have high pressure, that is high voltage, then you have to make fewer exchanges because you're exchanging big bills, $10,000 bills instead of dollar bills. So you can transfer a lot more pressure a lot more efficiently with a high voltage. The downside being the high voltage spreads to the rest of the environment a little too easily. It goes through other conductors too easily, like the atmosphere. So you can't go too high.
So V of B is 100 volts. What now is the current? Well, current times potential gives me power. And so my current is now 1,000,000 amperes. Alternatively, suppose that the potential at B in the wire is 100,000 volts, 1,000 times higher. Now the current is only 1,000 amperes, gives me the same power. In both cases, am I consuming at a rate of 100 million joules per second. But I square R, the heat loss on the way from the power station to me, is 1,000,000 times lower in this case than in that case, because I is 1,000 times lower. And the heat loss goes with I squared. And so now you understand why electricity, when it is transported from one place to another, why that is done at the highest voltage possible.
So the other problem with the exchanges, the dollar bill exchanges, is the more of those you make, the more exchanges you make, the more it actually happens that you're crippled by these obstacles. So the rocks in the stream become more and more important the faster the water's moving, the more turbulence is created. So it multiplies the effect of the resistance when you're making more and more exchanges. So it's not only bad, it's twice as bad. It's bad times bad.
When you get to Boston, you obviously got to do something about this enormous potential, because if you were to deliver 100,000 potential difference there, then half the population in Boston would electrocute.
Yes, and wouldn't that be good, though, right? I mean, this would be a good Darwin test. Just, winnow out the morons kind of a thing. So, yes, let's have all kinds of little tests that might wipe out half the population, and we'll all be better off, because it won't be the best half that get wiped out, generally speaking. I'd vote for it.
So now you've got to come down in voltage, which you do with transformers. We will talk about that later in the course. And so you bring it down to a comfortable voltage, which is in the United States about 100 and...
I think it'd be pretty cool to have 100,000 volts going into the house. I could think of all kinds of zappy uses. I need to weld something quickly. Poosh, 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 poosh. Be really nice to have a little plasma zapping wand in the house. Got to fly or something. Cool.
10 volts. In Europe, it's 220. So now comes the question, how high can you make V of A? The higher you could make it, the less loss there would be along the way. Well, you got to stay away from the breakdown electric field, which is the 3 million volts per meter. If at the surface...
Obviously, the 3 million volts doesn't really have anything to do with reality. So we already know that you can't go much over 300,000 volts without having substantial breakdown. So you got to keep it somewhere lower than that. Atmospheric breakdown.
Of these cables, you get 3 million volts per meter, you get corona discharge. That's a big loss. So you want to stay away from that. And so typical cables have about a radius R. This is now R is the radius of the cable of about 2 centimeters. That gives them a cross-sectional area, I think, of about 10 to the minus 3 meters square. That's correct.
So again, it's if you want to prevent the corona thing, it's all dependent on the radius of the wire. So the radius is again an effect here that atoms line up differently on small radius surfaces than they do on big radius surfaces. You can kind of understand that. Small radius, the alignment is more off than with a big radius. If I put a straight line on a circle, the smaller the circle, the more you're going to notice the straight line.
And the potential V at A is roughly 300 kilovolts. And with that configuration, you stay comfortably below the electric field.
All right, and the lines running here, they're carrying about 16,000 volts. Aren't more than a little more than a millimeter thick. They're not very thick at all. And but they can afford to be because they're only 16,000 volts. If it's a higher voltage, then there would be a lot of loss on those wires.
Of 3 million volts per meter.
But it's an amazing amount of total power that can be carried by those wires. I've seen them shorted, and it's an incredible amount of power coming out of a little millimeter round wire. Insane amount of power.
But you don't get the corona discharge. If the length of that cable, L, if that were something like 1,000 kilometers, not an unreasonable number, 1,000 kilometer distance from, if we get our...
I mean, it shakes the ground. there's so much energy in those cables. Literally shakes the ground.
Electricity from the Niagara Falls to Boston, not an unreasonable number. You can calculate now what the resistance of that cable would be. Because that resistance R equals rho times L divided by A. If you take copper, that has a resistivity of 2 times 10 to the minus 8 SI units. We have a length of 10 to the 6 meters of the cable, and we have a cross-sectional area of 10 to the minus 3 square meters, so that 1,000-kilometer cable would only have a resistance of 20 ohms. And to make the numbers a little easy, if we have a current.
They also have to consider, just throwing it in, the malleability of the metal, how much stress it can take, how brittle it is, how much weaker it gets with temperature. So there's lots of considerations in terms of picking your conductor.
Say of 300 amperes, then
The power that the power station produces.
if we take the 300 kilovolts for now, that power would be the 300 kilovolts times the 300 amperes, and that is about 90 megawatts. That's close to my 100 that I had in mind earlier. So you can calculate now what the loss is. The loss is I squared R. You know R is 20 ohms. You know I is 300 amperes. And so you'll find now that you have about 2 megawatt loss. That's not bad. 2 out of 90. So you have about 2% energy loss in transportation. You can also calculate now what the difference is in potential between the power station and Boston. VA minus VB is IR. You know that I is 300 amperes, and you know that R is 20 ohms. So VA minus VB is about 6 kilovolts. In other words, if the power station puts it on the line at 300 kilovolts, then you would get it here with only 6 kilovolts less. So it's not a very unreasonable situation. I told you that these power lines have to stay away from the 3 million volts per meter electric field, because then you get corona discharge. And when there is thunderstorms in the area, it can actually push up the electric field on the wire, and you can get corona discharge. I have seen that several times. Not only seen it at night with my naked eyes, that you see the power lines glow, but I've also heard it, because you can hear this cracking noise of corona.
Mostly, I guess, because the clouds are negative, so the thunderstorm's creating a difference in the potential between the wire and the sky, something like that.
Discharge. Very
Moisture, extra moisture in the air certainly doesn't help any. It helps with the conductivity, so.
fascinating, actually. I have a slide here which shows that. So here you see a high voltage power line, transmission line, and you clearly see the glowing of the corona discharge. They compare that with what's called the Roma's kite string. Kite strings at night, when you fly them near thunderstorms, can also produce corona discharge and light. That's why they call Roma's kite string candles.
That's probably why Benjamin Franklin thought you could use a lightning rod to dissipate the electricity that was going to be lightning, and therefore prevent lightning. Really quite brilliant.
Benjamin Franklin did quite a bit of experiments at night with kites near thunderstorms. Dangerous business, by the way. So you see that these high voltage power lines can go into a corona discharge. I now want to revisit our Leyden jar. We had a truly absurd situation whereby we did an experiment with a jar which you still see here, and I will redo the demonstration, but it's crying for an explanation because it looked like there was something wrong with physics. And I want to refresh your memory of what we have seen before and what this Leyden jar is all about. The Leyden jar is nothing but a capacitor with a dielectric between two conductors in the shape of a bottle, the jar.
Okay, so let's refresh that he actually showed as an image, a bunch of positive signs essentially, and put negatives on top of them so you couldn't see them, and then slid the image to represent what a dielectric is doing, or an insulator, or glass, that somehow the ions are switching because you're creating positives on one side and negatives on the other side, when both sides are independent and you have to put charge on them. They don't charge automatically. So just pointing out the misimpression left, that the insulator doesn't have a good contact in here. There's not a good communication from one side to the other. That's the whole point of being an insulator, is not communicating pressure.
Alright. And so the inner portion, which is glass, say has this shape. You see it there. You're going to see it shortly there. And then we have conductors, a conducting beaker around it here, and we have a conducting beaker on the inside. And we charge this up with the Wimhurst. This is the Wimhurst machine. And when we do that, we get free charge on the conductor. And so you get sigma free right here, and you get...
I don't know, like I said, I wouldn't call this free charge at all. It seems like the free charge is what's on the the insulator. The charge on the conductor needs a path to get off the conductor.
It's here, opposite signs of course. And you get sigma induced on the dielectric. Why do you get it? Because the dielectric sees an external field due to this sigma free. And so it begins to polarize, and so you get here induced charge, and you get there induced charge. If this side is positive, then the induced charge here will be negative, and vice versa. We have here a metal hook so that we can lift out the inner portion. So what we did, we charged it up with the Wimhurst, and then there is a certain amount of energy. The electrostatic potential energy of this configuration is 1/2 Q free times the potential difference, and the Q free is the charge which is on the outer conductor. And what I then did, I disassembled it very carefully after we had charged it up, took the inner portion out, took the glass out, the outer portion, and I took all the free charge off. I touched the conductors and discharged them. So that there's no Q free left, gone. The moment that is gone, the induced charge must also go away, because the induced charge is only there because of the free charge. Remember, the induced charge density is 1 minus 1 over kappa times sigma free. So if glass has a kappa of 5, then the induced surface charge density is about 0.8 times the free surface charge density. The moment that the free one goes, the induced one goes.
While they're in contact, but if you separate them, then none of that happens. So depending on how you separate them, you'll keep the charge on the glass. And it says 0.8, the charge that's on the conductor. So it's like you have now two charges, one that's 0.8 of the original charge, which is, say it's 10,000 is the original charge, you have 8,000 volts. But if you go by current or wattage, it's still, it's like you've created a duplicate power source in a sense.
And then I assembled it again, and much to our surprise, when I short out the inner portion with the outer portion, we saw a huge spark. That means there was energy left. And that is very puzzling. There cannot be any energy left.
So if you keep all of it on the glass without losing any of it, you'll end up with 80% of the original charge on the glass. So you could do this experiment and keep 80% of the charge is on the glass, essentially, because you're going to discharge the copper. Or the copper is going to be discharged by the disassembly.
Unless there's something wrong with physics. So I first want to show that again, to remind you of what you have seen before, and then I will make a proposal for an explanation. Let me check my light configuration. Oh, we're going to make it all dark. I can charge it up while you're seeing it actually. Yeah. Make it dark now. And now I will disassemble it. I take the inner portion out. The glass is a good insulator, so I don't mind touching that with my hand. Okay, and so now I take the inner conductor, touch it, lick it, kiss it, take all the charge off. There it is. Do the same with the outer conductor. Have it in my hand. For sure.
You can sort of assume that there can't be much charge left on them if you could touch them. I mean, 10,000 volts should be some kind of little sparky there. Should feel something.
Sure, there's no Q3 left anymore. On that anymore. I put the glass back in again. And then I put the inner core again. And now I'll make it a little darker for you because I want you to see that when I short this out, that you're going to see a spark. So I'm going to turn the light down. So look very closely. I'll tell you when I'm going to do it. 3, 2, 1. I'm approaching it now 0. And there's a huge spark.
Didn't see
That
it.
means energy. And that's crazy.
But you could hear it.
There shouldn't be any. And so some of you must have had sleepless nights not being able to explain this. Some of you actually wrote me email. You didn't have sleepless nights, I can tell that. So what's going on? There's only one possibility, and that is there must be free charge on the glass. How did it get there? Well, corona discharge. That's the only way it can get there. Keep in mind that the electric field in air, E in air, can be no larger than 3 times 10 to the 6 volts per meter. If it gets larger, you get corona discharge. In glass, by the way, it's a bit higher. It's 10 to the 7 volts per meter.
But the discharge is happening through the tiny air layer between the two. I mean, the two things are in contact, essentially. But the discharge, he's saying, is happening through the glass. I don't know. Maybe.
I will now make some calculations based on certain assumptions.
So it's sort of be based on probably the assumption of the thickness of the glass, because the corona discharge would have to happen through the glass.
And those assumptions may not be exactly accurate because I don't know the exact dimensions of this system, but the exact dimensions don't matter. What matters is the idea behind it, why it does such crazy things. So first of all, I will assume that this capacitor is just 2 parallel plane plates. That's a simplifying situation because it has the shape of a bottle. I will assume that the Windhurst produces about 30 kilovolts. I know that it's approximately right, but it may be 25. It may be 35.
Well, that's, could have just to put the ammeter on there just for fun, just to show how much voltage was actually on the thing and all that kind of stuff. So that might have been a little bit better, but anyway. So 30,000 volts is what we're starting with.
I will assume that the air gap between the outer conductor and the glass is 1 millimeter. That both are 1 millimeter. And I will just
well, we know that they're closer than that, so
assume that the glass thickness is 3 millimeters. And I take kappa equals 5 for the glass.
so that seems a crazily big number, 3 millimeters for the glass. I mean, that seems a little bit thick for a little beaker. But okay, let's play along.
So that is the basis of my calculations. So now I have here the conductor on the outside. This is the glass, and this is the conductor on the inside. So this is 1 millimeter thick, this is 3 millimeter thick, and this is 1 millimeter thick. And the potential difference of...
So again, clearly the copper is touching the beaker in places, so there's no 1 millimeter distance between them. He clearly had to tap the thing off. It's so close. So obviously this calculation might work, and it'll give you a number, but these numbers aren't really right, so frankly it just shows that the math doesn't really say everything that needs to be said.
Over the whole thing is going to be 30 kilovolts. But I know that the potential difference is always E times D. That holds for this gap, the local E times this D, the local E times this D, and the local E times that D. I also know that E glass is the same as E in the air divided by that kappa, which is 5. And I know that the total potential difference between here and here must be 30,000 volts. And so this allows me now to calculate in a very straightforward way the electric field here in the air, the electric field here in the air, and the electric field in the glass, because I get a simple equation with one unknown. And that's the following. I first go over this gap, and so I get E in the air times that distance, D, which is 1 millimeter. But of course later on, I have to go through this gap again, so I'll multiply it by 2 now. And now I have to add the electric field in the glass, which is the same as air divided by 5, times its distance, which is 3 millimeter. And that must now be 30,000, because that's the potential difference between here and there. That's one equation with one unknown. And I can calculate the electric field in the air gap.
So again, there is no millimeter of air gap. So this part is a little bit felonious.
The electric field in the air gap turns out to be 11.5 times 10 to the 6 volts per meter. It's here the same, of course, 11.5 times 10 to the 6. And here it is 5 times smaller. So I find here 2.3 times 10 to the 6. To show you that I did my homework correctly, the potential difference here is now 11.5 kilovolts. I put it here in kilovolts. The potential difference here is now about 7 kilovolts. And the potential difference here is the same, is 11.5 kilovolts. And if you add them up, you get 30.
Right. So this is completely dependent on these numbers, which it should be 2 millimeters for the glass and almost 0 for the other ones. So it's really all about the glass. But anyway, let's play along.
If you look at this cannot be, because a field of 11.5 times 10 to the 6 is way above the breakdown electric field. And so what's going to happen? You're going to get corona discharge from the conductor to the glass. And so what you're doing is you're spraying charge on the glass. And that...
But it's the wrong kind of charge, because the glass was negative. Let's say the copper is positive, the glass goes negative because the two are in association. So that's the theory. And now he's saying, no, what's really happening is the positive charge is spraying onto the glass, and now this glass is becoming positively charged. No, I don't think so. I think that it started off that way then. The idea that this surface here, the glass surface, was negative was wrong, because the copper's touching the glass. That's what's really happening. The dielectric is touching the other surface. There's no air gap. There's contact. So when the copper's positive, it makes this side of the glass positive, and this other side is negative. And it sprays the charge on from the very beginning. There was never any, this goes negative because this is positive. Yes, if there was an air gap, that would happen. But there is no air gap. So this explanation, I think, is wrong. So I think it's just wrong. And it starts with the false premise that the insulator responds to what's happening, this environmental thing where it's causing charge. Well, that might initially happen at a distance, but as soon as you make contact with the surface of the insulator, you're spraying the charge on all the places you're making contact. So all the places where the copper is touching the glass, or is incredibly close to the glass, it's discharging the positive charge onto the glass. So this becomes predominantly positive, not negative. See, that's why you should have a voltmeter on this thing. So, I mean, an ammeter or whatever, a voltmeter, then you could tell which way the voltage is, and you could, we'd know which way it was discharging.
That's the key to the solution of this bizarre behavior. And so when you later disassemble it and you take the free charge of the conductors, there is still this free charge which you have sprayed on the glass. I never removed that. It's very hard to remove because the glass is an insulator. It's very difficult to take charge of an insulator. It's easy to take it off a conductor. But I never even attempted that because I made you believe, as I believed myself for years, that once you take the Q free of the conductor, that there can be no charge on the glass. That is wrong because there is corona discharge.
Again, the corona discharge has to move whatever voltage it is to the other surface. That's the discharge. It's not discharge. It's not sending positive and creating negative. It's sending positive and creating positive. So the discharge is pushing voltage on, and it's pushing the same voltage as the copper. So the copper pushes its voltage onto the surface. Now the surface initially might have been a little bit negative, but as it pushes the positive charge on, it becomes way predominantly positive. The amount of negatives left on the surface is probably none.
So now comes the question, before we disassemble, what now is the configuration of the...
Be an interesting experiment is to create uneven surfaces and see if you can create patterns of electricity, where you have positive and negative charges on the same surface of an insulator.
electric fields and the potentials. I'll make a drawing here. And so now I draw again the conductor, the glass, and the conductor. I'd assume now that after the corona discharge, this field here is 3 times 10 to the 6. Maybe a little lower, but that's the maximum it can be. And so the field here in the air will be also 3 times 10 to the 6 volts per meter. But since I know that the potential difference between here and here must be 30 kilovolts, I can now immediately conclude that the electric field here is now 8 times 10 to the 6 volts per meter. That is the only way that it adds up to 30 kilovolts. Because the 3 million volts per meter gives me here 3 kilovolts. This here gives me 3 kilovolts. So now I need a potential difference here of 24 kilovolts. And that over 3 millimeters requires this field. Look, this field is stronger than that field. Whereas earlier we made the assumption that this field was 5 times lower than that field. Yeah, why is it now higher? Because we have sprayed right here on this surface, we have sprayed free charge. It's no longer...
So this example doesn't make any sense because he just drew the 2 copper conductors. He didn't draw the other surface. So you didn't spray anything, but you didn't draw the glass in there at all. So I don't know, whatever. Sorry, doesn't no. So the point is that as you remove the copper, it's the thing that's lost its charge. It's the thing that's become moot. 3 kilovolts. It's lost most of its voltage, and most of the pressure is now on the glass.
The field that is dictated by the external field and then the induced charges. That's no longer the case. It carries now itself free charge. You now have all the tools, maybe not the courage, to calculate how much free charge there is right here on the glass to get this field. It's a very straightforward calculation. And you will find that there is...
So I'm just saying, he's obviously redrawn it now, just gotten rid of the 1 millimeter airspace, and he didn't even draw the glass. So I just mean, it's just,
12 times more free charge here on the glass than there is here on the conductor. 12 times more. And so if I disassemble and remove the free charge on the conductors, I have almost done nothing, because most of the free charge is on the glass. And
alright, so now I see what he's saying. He's saying this one line is the copper, this one line is the copper. He's using this air gap again that doesn't exist, and this air gap again that doesn't exist. And he's saying the voltage difference between these two once it's corona discharged. So when it's corona discharging, it's losing voltage as it corona discharges. So as the charge is moved from the copper plate to the glass surface, the copper's giving up its charge. So it's basically just placing its charge on the surface of the glass. And likewise for the other conductor, it's placing its charge on the surface of the glass. And now, because it's a conductor, and the glass is saying, I'll take it, I want it, feed me. The glass is kind of saying that. That's the only way it goes off, right? The conductor says, I'll give charge to anybody who asks me for any. So all you do is get even close to me and be not a positive charge, and I'll give you everything I got, as long as I have more voltage than you. So as long as I have more than you, I'll give you everything I got. So it gives the glass, 80%, 90% of its charge, because it's not until it's given up 80% of the charge that the voltage gets low enough between the glass and the copper for the copper to say, you're now below my breakdown voltage. I can't break down anymore. At 3 kilovolts, I can't break down anymore. I can't send you any charge. And the insulator, who doesn't convey charge well, isn't going to corona discharge as easy, because it's got the voltage now and it's next to the copper, but it's not going to bother. It's comfortable, so it's going to keep what it has. I guess you'd yeah, that's enough.
I have not touched that. So now, if I reassemble, I have almost all energy left. I have not lost much. Lost some, but not much. And so what I should really have done, I should also have discharged the inner glass. That's not easy, but I will try that today. It's not easy because it's very hard to take that charge off. But I will try that. And then
Dip it in water or something.
And there shouldn't be much energy left if we reassemble it again and try to get a spark out. So I go through the same routine. I'm going to charge it up now. Okay. Take this cable off. Take that cable off. I take it apart. Do everything that I did before, the same way. Gone, old charge gone, whatever there was, old charge gone.
Okay, so it only has 3 kilovolts left on it, so that's why he doesn't feel anything. 3,000 volts ain't enough to make any sparky sparks.
Now this is more difficult. This is not enough if I do this. I have to get in there. Oh, I can actually feel it. It's a great feeling.
Yeah, see, so this one has 24 volts on it. So you just touch the outside surface, which is plus 24, and the inside is ground or whatever, but I just think there's a 24 volt difference between the inside and the outside. So obviously holding the outside and touching the inside, maybe you should feel something.
I can feel sort of a corona discharge with my... I have to really get everything out, and that's not easy. It's not. In fact, when I rub in with my shirt, I may even make it worse. I may be charging it up through friction, but I'll do the best I can. It's very indecent what I'm doing. Okay, so I try to get the charge now, something that we ignored completely before. This is really where the energy was, and I'm trying to kill that now. And so now I'm going to reassemble it, and I'll go through the same routine.
I would think if you just ran your finger around the edges, and then around the outs, you have to be able to absorb the charge. Your hand is a really good conductor.
Good thing I didn't break it. Put it back in again. I'll make it dark so that you can see whether perhaps there may be a little bit of spark if I didn't succeed to remove all the charges from the glass. So I'm going to short it out again. 3, 2, 1, 0. And I saw a teeny little spark. You may not even have seen it. So you have to conclude now that the physics behind this lies in the glass.
Alright, so again, his explanation, when he did the math and put that 1 millimeter as the distance between the copper and the beaker, that was just wrong to do. Because clearly when you reassemble it, you wouldn't be able to get the charge on the glass to the copper across that gap, if that gap even existed. So, there's a lot of not too good in that description.
And physics works even when it sometimes surprises us.
Yeah, well, it works because you force it to work, because you create air gaps that don't exist, and you do other little finagles, little cheats here and there to make it work. But your physics really doesn't work because you really don't understand the nature of the mechanics. And I'm just saying, that's frankly the obvious conclusion. You don't know what a charge is. You don't even know that the electron and the proton are the magnetic monopoles. So of course your physics can only work if you decide to put 1 millimeter where there's 0 millimeters.
See you Wednesday.
And that should be it. Didn't sign off as usual does. There it goes. Okay. Play the whole thing just to be, fair. Alright. So, another video completed. Another lecture completed. I'm not in the frame again, but whatever. Close enough. Probably close enough. Close enough for most people, probably. Alright. So anyway, till the next time. And such.